So for example, you know, let's say we're playing a game, flip a coin. If heads, I give you $5. You know, if tails, I give you $0, right? Sounds like a pretty good game. I don't want to play it, like, but well, if we switch the roles, it's kind of okay. But yeah, so right, so this is like a if x is the number of dollars I give, right, then probability that x is 5 is a half. Probability x equals 0 is a half, right? And like basic fact, probabilities have to add up to 1, right? So let's define, maybe it's just kind of a convenient definition. Let's define the range of a random variable. So the range of x is, so I'm going to write RNG of x. And that's just all the things that x could be with non-zero probability. So it's all the little x's such that probability that big X equals little x is positive. So here, like in this example, the range of x would just be the set 0 and 5, right? Because there's like no other outcome for this. I'm going to assume that there's a 0 chance if I flip a coin that it lands right on the edge or something, right? I mean, it always lands heads or tails. So, okay. So 2 key ideas that we're going to apply. So the first thing is, suppose I take a random variable and I compute its average. Actually, so before we write these key ideas, I actually need one more definition. So sorry, the expected value is like, well, it's the average, right? So it's, you sum over all the things in the range. So all the little x's in the range of x. You take little x times probability that big X equals little x. So this is the expected value or average or whatever you want to say, mean. And like if you apply it in this case, you're going to get 2.5, right? So you have half chance of getting 5, half a chance of getting 0. So it adds up to 2.5, which makes sense. Like if you have a 50-50 chance of getting 5 or 0, then on average you're going to get about 2.5, somewhere in the middle, right? Okay, 2 key ideas. So all of these are very basic principles, but they are kind of surprisingly powerful. So if the expectation of x is at most some number c, okay, so if I take a random variable, I compute its expectation or expected value. If I get a number c, or upper bound by c, then there has to be some choice of little x in the range of x such that little x is at most c. This is maybe easier to think of in the contrapositive, right? If everything in the range of x was bigger than c, there's no way that the average would be c, right? Like, you know, yeah, if we did this, if we did this kind of experiment and I told you the average is -1, that would be very strange because all the possible outcomes are bigger than -1. Like, that couldn't happen, right? Is this concept clear? If your average is the most c, then there's a choice where it's, and also if you switch the inequality, right? If you're at least c, then there's a choice where, it's at least c. Second thing, expectation is linear. So if I have a sum, like let's say a times x plus b times y for two random variables x and y, I can split that into a times expected value of x plus b times expected value of y. So yeah, all of this seems kind of basic, but actually, like, it's quite important to know how to use this. Like, yeah, often you might have like some random variable that looks maybe complicated, and you want to compute its expectation or expected value. And like, just doing it from the definition, like if you were to just try to apply this formula, it might be like really, really complicated. But then if you realize, my random variable can be split up into a sum of simple random variables, then, and I can apply linearity, I can just analyze each term of the sum. That makes your life way, way, way easier. So we'll see an example of that. Any questions about this stuff? Is there anything else I wanted to do? Okay, yeah, let's now talk about extremal combinatorics. So last time we proved Sperner's theorem. And this time we're going to prove something stronger, and the proof is going to be easier. So recall an anti-chain is a collection A of sets, so in 2 to the n, such that there does not exist A and B in A such that A is a strict subset of B. Okay, so what we're going to prove is the following theorem called the LYM or LYM inequality. So this is named for 3 different people who all seem to like discover this, but I guess none of them was really, I think this was like over a span of lots of different, maybe decades even, but no one was aware of each other's work. So anyway, it's Lubell. I mean, these names are not, you're not going to be tested on the history of these things, but Yamamoto and Meshkalin. So what it says is that for any antichain, A so the following sum, if I sum up from 0, k equals 0 to k equals n, I'm going to count the number of sets in A that have size k. So that's like A intersect square brackets n, choose k. And then I divide by n, choose k. Which you can think of as like a percentage, right? It's like a proportion, like, you know, A intersect n choose k could be 0 or all the way up to n choose k, right? So this is like a proportion of the like kind of kth layer of the power set. So this sum has to be at most 1. So yeah, I promised that this was that this implies Sperner's theorem. So maybe let's see why that's true first, and then we'll prove it. So the key thing is that this denominator, the biggest it could be is when k is n over 2. So for all the other terms, so if I take this, so to derive Sperner's theorem, so I'm going to write this inequality backwards. So I'll start with a 1 is greater than or equal to this sum And then, like I said, the biggest binomial coefficient is like the middle one. Okay, sometimes there's 2 of them, depending on if n is even or odd, right? But I can bound this below by, so I have the same numerator, and the denominator I just replace with n choose n over 2, right? Because if I make the denominator bigger, it just makes the whole thing smaller, right? And then I notice that this denominator doesn't depend on k anymore. So I'm actually really just summing the numerators, right? And that just gives me the size of A. Because, yeah, this is kind of partitioning A into the different levels. So this is just size of A over n choose n over 2. And now I just kind of multiply that over, and then A is at most n choose n over 2. So yeah, that's just by taking this thing, multiplying both sides by n choose n over 2. Is that good? Any questions about that? Okay, so like, actually this is like kind of a stronger, I mean, yeah. Like this also gives you information about, suppose I wanted, so like a anti-chain is a set that doesn't have any, no comparable sets, like under the partial order, like the subset relation. Let's say I wanted to not have any chains of length 3. You could actually kind of go through this kind of idea and figure out what the biggest set would have to be, what the biggest family would be with no chains of length 3, no chains of length 4, or any given length. By just kind of, okay, it's not quite, this step is not quite as simple as this, but then you just do a bit of thinking and realize, okay, I mean, the best thing to do is going to be to take the sets right near the middle of the power set. Anyway. Okay, let's prove this thing. So proof. So I'm first going to start with a definition. So let's say a chain is maximal. So remember, a chain is like a nested sequence of sets, right? It's the opposite of an anti-chain. So it's maximal. So this is going to be kind of like symmetric chains, except I'm going to say that it starts all the way at the empty set and goes all the way to the top and hits every level all the way. So if it contains sets, so this is a chain in 2 to the n, right? So sets of sizes like 0, 1, all the way up to n. So like, for example, maximal chain might look like this. It's got the empty set, the set containing, let's say, 3, the set 3, 5, the set, I don't know, 2, 3, 5, and dot, 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 all the way up to the set n. So there's a lot of, it's not clear what's in this dot, 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 but just anything, any set of size 4, 5, 6, etc., right? Actually, here's a question. How many of these maximal chains are there? How many ways could you generate a maximal chain? Yeah, that's exactly what I wanted to get at. It's, yeah, like you say, it's n factorial, right? Because you just could say, you could have a permutation where you say which element gets kind of revealed first, which is my singleton element, and then what element is added to get my set of size 2, and then what is added to get the set of size 3, right? So, yeah, basically, taking a maximal chain is the same as taking a random permutation. So this whole proof that I'm going to give, you could think of it in terms of maximal chains. You could think of it in terms of a random permutation. They're kind of equivalent. So yeah, there are n factorial. We're not really going to use this because I'm going to argue it a little bit differently, but it's worth knowing that there are n factorial maximal chains. Okay. So let's take a random maximal chain. And let's look at a set of size k. So let A be any element of n choose k, and let C be a uniformly random maximal chain. Uniformly random just means put all the maximal chains in a bag, stick your hand in the bag and like swirl it around and just pick one, right? So here's a question. What is the probability that A is an element of this chain? So I've got an arbitrary set of size. So you could think of this as the numbers 1 up to k. It doesn't really matter what this is. A is just a set of size k. Take a random maximal chain. What's the probability that that particular maximal chain, or that particular A, is in that chain? Any thoughts? I guess in some sense the fact that I'm saying it doesn't really matter what A is, right? I guess this must be the same for every set A. That's kind of makes sense. Why should a random maximal chain, why should it be biased towards some sets of size k instead of others, right? It shouldn't be able to tell the difference, right? But yeah. Any thoughts? What's this probability?
Is it just one over n choose k?
Yeah, how come?
Is there nk, or because the chain contains a set of size k, and there are n choose k possible sets.
Yeah. Yeah, exactly. So like when I take this random chain, yeah, it includes a set of every size. So it includes one of size k. It can't include two of size k. So it includes exactly one of size k. And there's no reason why it should be more likely to contain one over another. Like it's just completely random. So yeah, each of them should be equally likely. So that's 1 over n choose k. So that's like extremely small at the bottom of the board, but yeah, that's a 1 over n choose k. Right. That seems sensible, yeah. So maybe another question. So again, yeah. Again, C is a random maximal chain. So now I'll give you a question that has two possible answers, okay? So how many elements of A are in C? So C is, again, a random maximal chain. And yeah, it kind of has two answers. I mean, it depends. Where A is this original kind of anti-chain. What about anybody online? Can you see what the possibilities are for? So I'm asking, I guess, for the possibilities for the size of A intersect C. And yeah, there's more than one possibility, but there's not more than two. Any thoughts? Yeah, exactly, right? So 1 or 0, because we said this last time. If you have a chain and an anti-chain, they can't have two common elements, right? So yeah, this is either 1 or 0, so it's at most 1. Okay, so now I'm going to put these two things together and use those two key ideas, these probabilistic ideas, and we're going to get the proof. So basically, if I let x be this random variable, so C is a random maximal chain, right? This is a random variable. Because it's a number that depends on a random experiment, right? That's what we said. A random experiment picks this random chain, and then we compute this intersection, and that gives us a number. It always gives us 0 or 1, right? So the range of x is, it's a subset of 0, 1. I mean, it can't contain anything but those two values. So the expected value has, if you use the what's it called, contrapositive of the first key idea there, then that means the expected value of x has to be at most 1. Because yeah, all the values are at most 1. So So if there doesn't exist a number in the range bigger than 1, the expectation has to be less than or equal to 1. Okay, let's compute this expectation in a different way now. So basically, I mean, this is kind of the same as what we did for the Erdős-Corrado theorem. You take something, you count it 2 ways, and then, yeah, it turns out to give you the inequality. So like, this is sort of counting this expectation 1 way, or at least bounding it. And now we're going to count it a second way, using linearity of expectation. Is it okay if I cover this? It's okay. So yeah, the expectation of x, remember x is this A intersects C. Well, this random variable, I want to write it in a different way and use linearity of expectation. Because actually it's kind of hard to like, if I was to apply this, the definition of expectation to x, I have no idea how you would do it. I mean, but I can write this as a sum over all A in the antichain of an indicator random variable of A being an element of C. So here, what I mean by this is, so this indicator random variable is 1. So it's again a number, it's a random variable. It's something that depends on this random experiment. So it's 1 if A is in C, 0 otherwise. I'm really not organizing my board very well this time, but yeah, so it's, and now we can use linearity of expectation. Right. And this is quite a simple random variable. It only has 2 possible things in its range, right? It's always 0 or 1. So, you know, it's pretty easy to compute the expected value just from the, now on this one I'm just going to apply the formula for expected value. So this is like, you know, 1 times the probability that this indicator random variable is 1, which is the same as saying the probability that A is in C, plus 0 times the probability A is not in C. And we've already computed these kinds of probabilities. If I fix a set, the probability it's in the chain is just 1 over n choose the size of the set. So this is just the sum over all A in C, or sorry, in A, of 1 over n choose the cardinality of A. Which, if you just write it in a different way, that's the sum that we wanted. K equals 0 to n. A times A intersect n choose K over n choose K. Because basically there's this many sets of size K, and each of them will contribute 1 over n choose K to this original sum. But on the previous board, we said that this is at most 1, right? This expectation. So if you just follow it all the way through, 1 is at least the expectation of x, which is at least this, and that's what we wanted to prove. Right. So yeah, the fact that this is at most 1 is from the previous board, where we use this thing about the fact that there's only two possible values, right? 0 or 1. Okay, questions about that? So this kind of idea, it is something that comes up on assignment 2. You're asked to, like, I think, yeah, compute some probability of something, and then, like, use that to prove some inequality. And, you know, yeah, it's quite similar to this. And by the way, it's like we said, maximal chains are pretty much the same thing as permutations. So you could have phrased all of this for saying take a random permutation and look at the probability that a given set is a prefix of the permutation, meaning that set is the first, like, the first k elements are the elements of that set. And, like, the same thing would have worked the same way. Okay. So this is the limb inequality, and then there's, like, another kind of limb inequality called the local limb inequality. So for this, I need a definition. So for a collection, a family F in n choose k, where here we're going to let k be between 1 and n. The shadow of F is the collection. So we use, like, a little kind of, like a partial derivative kind of symbol, this kind of twirl thing. And that's, it's the set of all A in n choose k minus 1 such that there exists B in F where A is a subset of B. So this is something that is nice, you know, if you think about the picture again of the power set. If I think about, like, I've got some family F living on level k. So this is like n choose k. Right. The shadow is like you kind of shine some light from the top of this poset, you know, and well, okay, maybe that doesn't really make any sense. Basically, you look at the things that you can get by taking an element in F and deleting one element. So it's all the things kind of directly below in this poset something in F. So yeah, this would be the shadow of F lives in n choose k minus 1. And yeah, it's all the sets that are directly below a set in F. Okay. So the local limb inequality says if F, well, or for any F, in n choose k, where k is between 1 and n. So if I look at the shadow of f as a proportion of n choose k minus 1, so I take the ratio of the shadow divided by n choose k minus 1, that's at least the kind of proportion of f in n choose k. So the size of f divided by n choose k. So like, in some sense, this is saying that the shadow of a set, of a collection kind of gets bigger, well, not bigger, but not necessarily bigger, but bigger as like a percentage of the place where it lives, which is n choose k minus 1. Right, so yeah. This takes up a bigger percentage of this than f does of its own level. One kind of interesting thing about this is like, this is completely equivalent in like a very strong way to the LYM inequality, but this doesn't like say anything about anti-chains. It's kind of weird, but yeah, in any pose set, basically, if it satisfies a version of the LYM inequality, then it must satisfy this and vice versa. So these things are quite strongly kind of equivalent to each other, even though it doesn't really look like it. So what we're going to do is use the LYM inequality to prove the local LYM inequality. So, one thing about this is like f lives in a level, right? So f is an anti-chain by itself. So basically, I want to kind of augment f to get an anti-chain and then apply LYM to it, the LYM inequality to it. I better not, like if I take something in f, I better not add any things in the shadow of f to it, because that's definitely not an anti-chain. Literally, the things in the shadow of f are like the subsets of these ones, right? But as long as I take f and I kind of augment it by putting the stuff that isn't in the shadow, like is in this level but not in the shadow, that's going to make an anti-chain by definition of the shadow, right? So that's what I'm going to do. So let A be f union all of n choose k minus 1 except for the shadow of f. Well, then this has to be an anti-chain. Well, why? Because, if two elements of f can't be nested inside of each other, they have size k. Two elements in here can't be nested inside of each other, they have size k minus 1. And you can't have something here that contains something here, because that's by definition of the shadow. We excluded all of those. Is that enough of an explanation? Yeah, if you think about, you can't have two things here that are contained in each other. You can't have two things here. You also can't have one thing here and one thing here. So, so by LYM, LYM inequality, if I sum over all the different sizes and basically there's only sets of two different sizes. There's sets of size k and k minus 1. So basically, LYM tells us that this plus the size of n choose k minus 1 minus the shadow n choose k minus 1 is at most 1. So this is applying LYM to, so applied to A, the anti-chain A, right? Because, yeah, there are only sets of these two sizes in A. But this left-hand side, we can just kind of do some substitution, right? That, like, this is just n choose k minus 1 minus the size of the shadow. Then a bit of algebra, right? This is like a 1, which will cancel that 1. And then you've got negative of shadow over n choose k minus 1 if you put that to the other side. So therefore, f over n choose k is at most shadow of f, cardinality over n choose k minus 1. Okay. Any questions about this? It's good. Okay, so one thing about this local LYM inequality, it's nice, but actually it's quite the form of it is quite beautiful, I feel like. You know, it's a proportion in the sets of size k minus 1 and sets of size k. The thing is about this, though, it's not necessarily tight, right? So like the inequality it gives you is something like the shadow of f. So if I just wanted to say, how big must the shadow, actually maybe I'll state this as a proper kind of problem. So this is what we're going to focus like the next maybe 2 or 3 lectures on. So for, let's say, integers 1, k is between 1 and n, and let's say m is between 0 and n choose k. What is the minimum possible size of the shadow for a family f in n choose k with size equal to m. So by local LYM, that gives us a bound that the shadow has to be at least m times n choose k minus 1 over n choose k. But that's just a bound, right? Like I said last time about the assignment questions, when I'm asking, what is the minimum or what is the maximum? Well, a bound is good, but that doesn't determine the minimum, because if this bound can't be achieved, then it hasn't determined the actual minimum. So yeah. So basically, we want to get, so this gives a rough answer, but we want an exact answer. Well, maybe want is a strong word. I'm not sure if anyone else wants it, but but that's what we're going to get. So that's something called the Kruskal-Katana theorem. So the next topic is, Kruskal-Katana theorem, which gives us the exact answer. k, m. So like every single choice of parameters, we're going to get the right answer. This is going to be like kind of order of magnitudes more complicated as a proof than the other things we've done. So it's going to take like maybe two or three classes to do it. But yeah. So it's not one of these nice, quick, like short and sweet arguments.